So the problem with integration is sometimes it is so hard that it might not be possible given what we know. So it says in many cases, the general solution to a first order differential equation is not possible. So then we use other methods like slope fields to obtain information about the solution. So what we're going to find out here is we can graph a basic idea of a solution, even though we don't know what the equation of that graph is and what that looks like. Now, here's a differential equation. dy dx equals 2x. It is a fairly straightforward one. Could you work backwards from that? Could you integrate that and tell me what the original function is? Absolutely, right? If we integrated that, here we go, if I integrate this, are we pretty good with that? Good. So it's a really straightforward integral. Now, what a slope field does is it takes all of your points that you have in the whole graph and draws many tiny slopes. For example, if I take this point right there, that point is 1, 1. The x value is 1, the y value is 1. In this differential equation, you see that you only have x's. There is no y's, but some differential equations you're going to have x's and y's. And sometimes they're separable and you could still find the equation, but sometimes you won't be able to separate the x's and the y's and you won't be able to solve the integration. But what we're going to do is we're going to take our differential equation and plug in x is 1 and y is 1. In this case, there's just the x. And when I plug in x is 1, I get 2 times 1, which is 2. And we draw a tiny little line there with a slope of 2 as close as possible that we can think of. Right? What does the slope of 2 mean? A rise of 2, a run of 1. We draw a little line that has a slope of 2. Can you see that if you plug in any of these ones, you see how they're all the same slope? All of these lines here. Why do they have the same slope? Because all of those points would have an x-coordinate of 1. The y-coordinate changes, but there's no y in this equation. So all of those slopes will be little tiny slopes of 2. If you plugged in 0 for x, do you see that you would get a slope of 0? Slopes of 0 are flat. You see that all of these ones are flat. So now if you did the tedious work of every single x point drawing the slopes and every single y coordinate, if you did the tedious work of doing all those many little slopes, you make a slope field. And the beautiful thing about a slope field is this. You throw in a random point. Okay? Can you pick me a random point that's on this, somewhere on here? Negative 2, and then 2, that would be this point right there. Okay? So what you're going to do is you are going to move from that point and draw the graph. And the way that you can do it is say, like, okay, my slope right now is about there. So now if I'm going in that direction, I hit this one and my slope turns there, and then I hit this one. Oh, and then I follow my slopes. Did it make a parabola? Crazy. It made a parabola with its vertex, looks like at negative 1.3, which means my C value for that point that you chose could have a vertex at negative 1.3. Or maybe maybe I should have, maybe my curvature was a little bit off. Maybe it worked out perfectly to be at negative 1.5. But just having a point and following your slope fields, and I don't know, I think maybe I bent it a little bit here. I probably should have followed this slope, and maybe I should have gone a little bit deeper into it. But I get an idea, and no matter which point you pick in here, it'll draw different parabolas every single time, which is kind of neat. That's the idea of a slope field. And here we have two figures. Well, we have the same slope field for the differential equation y prime equals x minus y plus 1. This one, you can't separate the x and the y with multiplication. There's no way for us that we know of right now to integrate this easily. So the best we can do is take that equation and pick different points and draw many slopes. So some things I look at when I'm looking at a slope field, do you see all these flat ones here? What happens in a flat one? Like, I'm going to assume we're going over by 1, up by 1, and just do a double check. So this point here normally would be the point 0, 1. Does it work out when I plug in 0 for x, 1 for y? Does my slope end up being 0? Yes. In fact, all of these points are points where if you plug them in, you get 0 for y. And that's why those are all flat. Now the second diagram says if we went through 0, 1, the slope would be flat there. So I would definitely have a minimum. Okay, then my curve would go along and it keeps hitting these slopes. And it seems to follow that, once it hits that slope, and that slope stays the same, it seems to follow that line. As I go this way and follow the slopes, it seems to go up in that direction. And so now this is the solution. That graph, which I do not know what its equation is the solution for that differential equation, even though we couldn't integrate it. Then, of course, we could take that graph and we could play around with equations and see if we could find something that does match up with that and say, I think I found a model that works for our situation. So how do we come up with that slope field that we just saw? We take a bunch of different points. So you've got this chart here, and you plug in the x and you plug in the y, and you could find a bunch of different slopes. Then for each of those points, you draw those slopes to the best of your ability. Higher number, steeper slope. Negative slopes go down from left to right. Positive slopes go up from left to right. So while you're writing some of these down, I'm going to take out my highlighter and just connect you to a couple of these. So for example, that information is that slope. I go to my point, -1, -1, because that's my x-coordinate and my y-coordinate. I found out my slope is 1, so I drew a little mini slope with a slope of 1. Zero, 0 is an easy one to pick out. When I plug in 0 and 0, I also get 1. It ends up having the same slope as that yellow one. Zero comma 1 is kind of interesting because I get a slope of 0. A slope of 0 is a flat line. That's why that one matches up with that one. What's the steepest one? I'll go to the steepest one here. Looks like 1, -1 has a slope of 3. That's my steepest line on my graph. So you're plugging in your x and your y, that's your coordinate, into your differential equation. That gives you a slope. Technically, that's the slope of the tangent line at that point. If you had a graph going through this purple line at this point, it would have to curve like that, and that would be touching at that point. That's your tangent line. Your little slope field is your little mini tangent line at that point. And then based on that, you would see where this graph goes. Like this graph would go here, turn this way, and eventually flatten out. So fill in some values for the next ones and draw your slope fields. And I'm just going to put up the slope field for the next one. So you can check your lines. If your lines match up with mine, then your numbers in the column will have matched up. But I don't want you to check the numbers because then you're going to be looking too long. Did you see that some of these were undefined? That would cause you to divide by 0. So how does that show up on our slope field? We have straight up and down lines. The function might still exist at those lines, right? Just because the derivative is undefined. We think back to critical points, right? That might be on your original graph a sharp point. It might be an asymptote. Maybe the original graph is not allowed. So if you had straight up and down lines all the way along an x-axis, that would kind of imply that you have an asymptote there. Does anyone remember doing this equation when we did separable? Do you remember what equation we got? A circle. And check this out. I did those tangents and went to each one. I'm actually really quite impressed with my circle. That's like, that makes me happy. That's one of the best circles I've drawn in the last 78 days, I'd say. This little hair is kind of bothersome, but other than that, not bad. Okay. Take a look at this one. I'm drawing more of it than you would see. But if you multiplied it out, you would get x squared plus 2x. If you integrated that, you would get x cubed over 3 plus x squared plus c. And I would get that x cubed graph in the end. Depending on where I start drawing my graph, gives me one of a different x cubed graph, moved up or down. But it would be the same x cubed graph no matter what. All the next question. All right. As far as students go, when you see match, generally you have a little bit more of a smile than if you saw the first word was graph, right? Or even solve, or evaluate. All of those ones seem like matching is, I don't know. Isn't it always kind of a more fun kind of task to match? Feels like you can cheat a little bit and not have to show as much work. So look at those slope fields. Which one is the slope field for each of those? Have some fun matching. All right, some of you are done, some of you are stuck, some of you are in the middle, so let's talk some strategies. One strategy you can do is if you can actually find the solution. What is the integral of sine? Negative cos plus c. So one strategy is if you know what the integral is, a negative cos graph, could you find one where if you put and follow the curves, that matches up? You see how I follow the slope lines? And wait for it. Oh, what? I don't. What? There. Perfect. I guess I kind of gave away 5. No. It's going to be E. First pattern I want you to notice with slope fields. Slope fields that only have an x, like the first one, it only has an x, which means the y coordinate does not matter. If you look horizontally, or no, sorry, vertically in columns, do you see that all the slopes stay the same in every column? All the slopes will stay the same in every column because the y coordinate does not matter. You have that, you're still plugging in the same x coordinate every single time. So all of these equations that have only x's, your column will stay the same. So if you look at graph A, do you see that your column changes? The slopes change in the column. This one has to have a y coordinate or a y value in its slope field. Similarly, if it stays the same horizontally in rows, you know that you don't have any x's. So do we have any, like G? I'm going to just highlight them right now. I'm going to highlight them in yellow because I'm not going to decide. Well, I already know G is 5. Notice there's no x in that one. Any other ones that stay the same straight across? Look, B stays the same straight across. Is that the only other one that stays the same straight across? Is there only one other equation which has just y? I'm going to go with number 4. Tempting to click right here. Wow! That's terribly disappointing for me. If I clicked right there and I was, what the heck? Ah, it's way up there. That makes sense. It is B, and I gave away 8. That's not a good idea. Okay. All right. So we have those things that are changing. So now, just as far as color coding patterns that I notice, connected to ones that are changing both vertically and horizontally. Do you see that this one, F, doesn't have same columns, doesn't have same rows? This one, A, doesn't have same columns, doesn't have same rows. Straight up and down, straight across, different. This one's the same across. This one's same up and down. Not same across, not, okay. That one is different, up and down, and left and right. So A, D, and F are going to have X's and Y's. So as far as looking at which ones have X's and Y's, those are going to match up with 6, 3, and 8. So we can do some preliminary strategies that way. Okay? Other preliminary strategies. I like horizontal tangents. I like non-permissible value ones. So then we can look at things like which ones look like they have non-permissible values. That one looks like it's going to make a circle. If it makes a circle, there will be a tangent here that's straight up and down. A non-permissible value. Are there any differential equations where you would have y values you're not allowed to plug in? Or x values you're not allowed to plug in? And that looks like number 6, which apparently if I click on number 2, it works. And that matches up with A. mental math wise, we can do some easy mental math. You see that if I put in 1, -1, I would get 0. So if I went to one of my green graphs and I went to 1, -1, I would say, does this one look like it should have a flat line there? Or does this one look like it should have a flat line there? I feel like F is a way better choice. So then I'm going to say, because I checked.
You highlighted -1 negative.
Oh, I highlighted the wrong point. Thank you. I was like, why is this? I wanted to highlight 1, -1, which on this one would be over there. And this one is, yeah, oh, I totally threw myself off because I highlighted the wrong point. Confused there for a second. Yeah, if I plug in 1, -1, and actually graph it in the right spot, then D seems to match up, right? And this one doesn't look like the slope field at all at that point. So then that becomes D, and that becomes F. So we can use specific points and plug them in to check things on our slope field. Now these slope fields, they were done purposely so you didn't know exactly the scale and you didn't know the points. So you were kind of doing a little bit of guessing there. All right, we don't have many left to go, but if I wanted to just look at number 2 and see what I could find out. First of all, number 2 has only x's, no y's, so it should be the same all the way up and all the way down. So we've got, what's left now is we've got C left doing that, we've got H left doing that. And you could just plug in a number. I really like 0, 0. Because it is a good starting point. If I plug in 0 into this one, do you see that you would get a slope of -1? So I'm going to look across all my graphs and see which ones at 0, 0 seem to look like they have a slope at -1. I do not, oh, sorry, I do a positive slope. There we go. I'm like, ooh, I kind of like that one. But it almost doesn't look steep enough. All right, got something there. Which are the ones that I have left to check? Those are the only 2 left. So I kind of like this one, but I didn't feel like the slope enough. This one, it looks like it's switching. Does it switch at that point? I might still be unsure. So I go and I check some other slopes, right? As the x value in number 2, as the x value gets bigger, what do I get? If I look at this one and I integrated it, right? Both 2 and 7 should give me parabolas, right? Oh, well, sorry guys. I'll give you the answer. That is the process of thinking through these. On your way out, I have got your second take-home quiz. It is on the table here. Make sure you grab one.
You know, I always talked about doing the quiz and I forgot to